Okay, so I think we will get going. People may join us. The call is being recorded, so people will have the opportunity to listen back. Or if you do miss the call because you weren't able to attend, then that will be your opportunity too. So let me introduce our webinar. So today we're going to be hearing about smart maintenance. It's a topic of interest to BioPhorum, and we're going to be hearing from 4 presenters whose cameras you can see on the screen, and they're going to be talking about different aspects of smart maintenance. And then towards the end of our time together, we'll have a time for Q&A as well. So BioPhorum, for those of you who don't know it, it's a membership organization. It helps biopharmaceutical companies think about problems of common interest in a non-competitive environment. And smart maintenance has been a topic of interest for us for a few years now. In earlier work, we've managed to produce a smart maintenance overlay for the digital plant maturity model, which you may have come across. And on this slide that you're looking at, there's a link to that information on the left-hand side, and you can QR code access it as well if you prefer. And then more recently, on the right-hand side of this slide, we've published a document that talks a bit about the architecture and the data-driven approach to smart maintenance. And we'll be talking about the content of that paper in the call today. But we will also explain a little bit of that historical perspective. And as well as thinking about that particular paper and sharing some of its content, we'll also be hearing a case study as well from one of our member companies. So let me just introduce our speaker panel and just give you a layout of the agenda for today. So when we're done with the introductions, then Celine will introduce herself, but talk a little bit about that smart maintenance overlay and the business outcomes that we can get from smart maintenance. Burkhard is going to talk to us a little bit about predictive maintenance levels, so thinking about the sort of increasing maturity of that and some of the kind of practical and real-world KPIs that are important in that space. Jonas is going to help us think about how do we do this stuff. So thinking about how the practicalities of the architectures and setting up the right environment can happen. And then Niall is going to talk a little bit about his Janssen experience and some of the things that they're looking to do there. So with all of that said, I'm going to just quickly talk about a couple of things around the content. So if you are on Teams as you are, you'll see this control panel. So a couple of things. Firstly, please put your comments, your questions, extra topics in the chat as we go along. Happy to have all that interaction. If you are wanting to speak or to appreciate, then, just please pick up these comments to do that. What I'm hoping that we'll do as part of the pattern of this is, basically speaking, we'll end up letting the speakers present their materials for most of the piece, and we'll pick up the substantive Q&As towards the end. But please, as I say, put those in the chat. If there is something that's about kind of comprehension or just clarification, then as we move through each of the sections, I will try and pick those up in the chat and just ask the question of the speaker before we move on, just so that those sorts of pieces can be picked up. But a more substantive question about the content we'll leave to the Q&A, if that's okay. So with that said, I'm going to pass over to Celine. So Celine, please introduce yourself and take us about the smart maintenance overlay and planned business outcomes.
Thank you.
Yeah.
Thank you very much. So I'm the IoT lead for equipment services within Cytiva, which is the global providers of technologies and equipment that helps advance and accelerate therapeutics. If you can go to the next slide. Thank you. So I've been working in equipment services for life science within many years. And when I discuss with pharma companies and my colleagues as well, they all want the same, more or less. I'm sure you will recognize yourself. They are all under pressure to achieve more equipment availability and performance with less maintenance program cost and time. So the BioPhorum group identified those needs and published also a first paper about smart maintenance with key players in the industry, with some who are here today. I invite you to read it. It's super insightful. First, this paper defined what smart maintenance means, and I think we all have different definitions in our mind, so it helps. It highlights also numerous benefits, whether it's about intensifying the capacity of drug production by increasing equipment reliability and plant availability, or reducing costs by minimizing unplanned downtime, or even have a sustainability target by improving energy efficiency. Actually, McKinsey did an extensive report in 2018 and reported that manufacturers of technology in the chemical and the pharmaceutical industry have the potential to gain up to 15% plant uptime and to reduce maintenance costs by up to 25% if they apply smart maintenance capabilities. And Burkhard, who is here today from Merck, is going to give you later more KPIs specifically linked to the pharmaceutical industry and to the experience at Merck. You go to the next slide. What I also like about this paper is that it gives readers a tool to assess our way of working and level of digital maturity with respect to equipment maintenance by mapping the digital plant maturity model so that we can assess in our own company and make a case for investment to justify adopting those higher level of maintenance practice. So on that slide, you see the DPMM. So level 1 is manual, paper-based process. The maintenance is pretty much reactive. Level 2 is the beginning of automated maintenance planning. And we see with my colleague that 95% of those companies are at this stage with respect to maintenance. And only a third really get to the next level, level 3, when the plans start to be connected together with higher level of automation, integration, and really where we see people starting to work on condition-based maintenance, meaning using sensors to assess the current condition of the asset and the critical components. And this is where we see companies starting to think about IoT connectivity and further modernizes for critical components and equipment. Level 4 and level 5, to me, are still a future state for the pharmaceutical industry, and that's why we're here today to see how we can implement that. So level 4, it's all about predictive maintenance. So that means connected to the cloud. The plan is to use real-time condition monitoring data, operational context of the production site, OEM global threshold recommendation, and maintenance logs to build algorithms so that we can predict equipment failure and therefore about downtime. And for that activity, we believe with my colleague that the partnership between the pharmaceutical companies and OEM and suppliers is essential to develop a data lake of information that will fill the predictive model and provide meaningful recommendation. Also, I think in our companies, depending on our equipment and criticality, we'll have a blend of maintenance approach with a cursor on sensor-based maintenance and cloud-based solution as we move forward. And if you go to my next and last slide, thank you. And I will finish by this. To get from one level to another in the DPMM, what it's important to consider, what we're thinking of considering is a transition. Our software, hardware systems, and processes, they will need time to change and adapt as we move. So trying to move all of them at the same time, I would say is not recommended. So for instance, in our company, we're starting with the critical assets. Also, something super important, teams will have to adapt as well. So an active culture change program needs to be included in the transformation activities. Otherwise, it's difficult to succeed. And finally, and I'm going to repeat that again, to move to condition and predictive maintenance, we will need to be open to cloud-based connectivity, IoT, and start developing a data lake together between OEM and pharma companies. And that's what Burkhard, Jonas, and Niall will explain this in greater details today. Thank you.
Tim, you're on mute.
Thank you very much. My apologies. So thanks, Celine. We're going to hear from Burkhard now, who's going to explain a little bit about predictive maintenance levels and some of his practical experience in Merck. So Burkhard, if you'd like to introduce yourself and talk us through your materials.
Thank you very much. You hear me?
Yes, we can.
Okay, good. Thank you very much, Tim and Celine, for this nice introduction already. I'm working for Merck in the pharmaceutical division and overlooking the maintenance management in a network of 16 sites distributed a little bit over the world. And please go ahead. Yeah, what I'm talking today to you is about the two questions. Where do we situate ourselves with predictive maintenance or with smart maintenance with respect to what we have done before? And secondly, what measure can we take to see if it is successful? Meaning the highest level that we're always asked to provide is what are at the end the savings that we can expect? Not easy question, we tried. So what we see here is the endeavor of all this is to go beyond reactive and time-based maintenance, what we all know from, especially from pharmaceutical or biotech operations, and apply more and more predictive and prescriptive maintenance types where possible. Here you see a busy slide with all these maintenance types and characteristics of these maintenance types. We concentrate on the levels 7 and 10 here until 10, which is also the core of the section that Jonas will provide to you. Now, where are these situated with what we always did before? Therefore, please go to the next slide. Here you see in green what we are going to explain a little further, but let me take you up the ladder, we call it, or the levels of smart maintenance approaches, starting from reactive, that means run to failure maintenance, until the very end, the self-healing plant, where a robot will carry out the maintenance for you, something similar to what you see behind me in my video background here. So reactive maintenance, we all know it, is usually associated to urgent maintenance, something breakdowns, production stops, you don't have a redundancy, and it's a kind of the worst case of the failure pyramid that you can imagine. Next better level is you have a redundant equipment and you can switch, so production doesn't stop, and you can repair the equipment, still probably in urgent mode, but you can repair it. Then we all know plannable corrective maintenance. Usually it's triggered by our computerized maintenance management system, CMMS, by a user notification. Still, it's not urgent, it can be planned. That's already a good case, but it's still based on human judgment. What we often do for GMP reasons is time-based maintenance. Even most of our money goes into that category. It's a rigid schedule where you always do the same thing, regardless of the state of your equipment. A bit better then is a runtime-based maintenance. You don't have a rigid schedule, but one that's based on the hourly use or the daily or monthly use of the equipment. So number 6 is referred to condition-based maintenance in the sense that there is a visual check and control by a technician. We are looking at the status, but we don't have a sensor to tell us what is the state. It's still a human judgment. Now, when we replace that human judgment by a sensor, we are stepping into the sensor-based world. That is a pre-requirement to become intelligent. This is number 7 here, and we call it predictive maintenance basic. Usually, you have a technician who's walking around with a handheld device, checking with this the health of your equipment. Once you have that sensor wired, hardwired, you have a continuous supervision, and you can set alarms and thresholds. That is already more advanced. Number 8. Coming to smart, you still need something that can be called artificial intelligence, a brain, a neural network behind. That means we are putting together several sensors in order to get information, or we have learning systems that can interpret the data. Once you have that in place, it's only a small step to go to prescriptive maintenance. Here, the system will not only tell you that something needs to be fixed, but also exactly what needs to be fixed and how it needs to be fixed. And once you know that, you can imagine sending out a robot with that information who's able to do the job. Saying this, we will not have one kind of maintenance in a plant. Probably our plants are so complex that we will find, even if some is already level 11, we will still find some run to failure approach as well. Next, please. Yes, and if it's not to repair our robot, who then needs to be repaired, mostly in urgent maintenance mode by a human. Next slide, please. So what can we expect now? What is the upside of all of this? High level, we can say we have reduced unexpected equipment failures, reduced downtime. Maybe we have fewer lost batches with that, and greater production leads even. Then we have lower unplanned corrective maintenance cost, reduced preventive maintenance cost, lower operating costs thanks to increased equipment performance, and also a better use of our expended capital. Next, please. Okay, so where more specifically can we expect the savings? We have sat together and we aligned ourselves on this approach. So it's based on the experts' view that have been working together here. We can, if we are able to apply large-scale predictive maintenance approach in future days, expect to drive down urgent maintenance, and a reasonable assumption is to save cost associated to that by 20 to 30%. Likewise, we can also save the plannable corrective maintenance because we have better information from the sensor on when a replacement should be scheduled. But most importantly, we can also act on our time-based preventive maintenance. We have assumed a cost reduction by 10 to 20%, mostly by extending maintenance cycles that are fixed today. They will stay fixed, but they will extend their cycles. Next slide, please. We have done simulations knowing where our maintenance costs occur in our type of plants. We have put two types of plants together here. One is a more, I would say, reliable, newer type of plant. You find it more in the biotech world. You see here the blue bars. They come out of the distribution of preventive maintenance, corrective maintenance, urgent maintenance, and also cost that are due to downtime of equipment that occurs on the customer side, on the production. And you also have here another distribution of cost, possible cost saving, coming from a less mature side, where you have less preventive maintenance and more corrective maintenance. The good news is that in both cases, you end up in an average of 13 to 15%. But you see very clearly, you have to take into account from the start the reduction of your preventive maintenance and your also plannable corrective maintenance. Next slide, please. Okay, sorry.
That's okay. Burkhard, thank you very much for that. So really helpful to hear what's going on in real time, if you will, and in the sort of real world in terms of practical experience. So I'm going to ask Jonas to take us on a little bit more and explain, some of the challenges that are about putting this sort of solution into practice and some of the things that can be done to overcome. So Jonas, please introduce yourself.
Thanks, Tim. I'm Jonas Birch, the Senior Director of Applied Technology at Emerson, which is an industrial automation solution provider. This means I'm responsible for helping plants, transform how they manage maintenance, reliability, and sustainability. So yeah, first slide, please. So why haven't plants already implemented smart maintenance to reduce maintenance cost and downtime, as well as for improved sustainability? Well, because most plants lack the automation required for smart maintenance practices. Current limitations include, smart communication not enabled for instrumentation, equipment like pumps not fitted with sufficient sensors. There's no secure connection from plant automation systems to computers in the office, mobile devices, or to the cloud. Non-standard system interfaces and information models prevent data flow, and third-party app installation is not permitted. Unfortunately, many new plants are being built with this same limitations. So plants need to fix this to transition to smart maintenance. Next, please. So how do plants transition to smart maintenance? That is, to perform maintenance and reliability work in a smarter ways. Well, people need new tools with new capabilities, such as descriptive and prescriptive analytics for condition-based, predictive, and prescriptive maintenance, using data from existing control system and new add-on sensors, while preserving the GAMP validation and preserving the control system robustness and safety. And all of this without compromising cybersecurity. For simplicity, a single infrastructure is shared for sustainability, safety, production, and quality management. Plants have systems that have long life cycles. So interoperable standards are used to stave off obsolescence. And it's built on familiar automation technologies to be easy to use, to minimize the adoption learning curve, and to become a natural part of daily work practices. And it's modular to allow use cases to be addressed one at a time. And it is scalable, to enable plants to start small and then scale out fast. So yeah, next slide, please. So what do plants have to do to enable smart maintenance? Well, system architecture for the additional automation is modeled on the Namur Open Architecture, or NOAA. A key principle in NOAA is that the core process control, or CPC zone, is independent of the additional monitoring and optimization, or M&O zone. Think of the CPC zone as the existing GAMP validated systems like the historian, the process automation system, and its sensors and actuators. So this independence ensures the sensors and software in the new additional M&O zone does not impact the safety and robustness of the automation in the CPC zone. And it enables changes to be made in the M&O zone without requiring new GAMP validation of the automation in the CPC zone. Equipment manufacturers can be granted access to the M&O zone to manage the condition and performance of their equipment, like pumps. Next slide, please. So the GAMP validated process control strategy sits in the CPC zone. The plant historian is typically part of the GAMP validated system and therefore part of the CPC zone. Some predictive maintenance use cases may require data from the core process control automation system, for instance, pump discharge pressure. NOAA uses the OPC interface between the CPC zone and the M&O zone. OPC UA servers are deployed in the GAMP validated CPC zone if not already available. It may not be convenient to add OPC UA servers in the GAMP validated automation system in the first phase of digitalization. In this case, it can be added later. Note that digitalization can start with the many predictive maintenance use cases which do not require live data from the CPC zone, because most of the data come from the new non-process sensors such as vibration and acoustic noise. So this will not delay digitalization. Next slide, please. Automation for predictive maintenance is included in the plant M&O zone. That is, additional sensors and software used for predictive maintenance are installed here. We'll deep dive on all of this in a minute. Next, please. Some predictive maintenance activities may be carried out from a central maintenance management hub covering multiple plants. M&O automation tools covering multiple plants are implemented in the central M&O zone. The interface between the central M&O zone and plant-specific M&O zones is also OPC UA. Cybersecurity is provided for the communication between plant-specific M&O and central M&O. Next slide, please. There are 3 NOAA interfaces from the GAMP-validated CPC zone to the M&O zone. The primary channel carries data from the control system. Since the control system is GAMP-validated, it does not accept data in the reverse direction from the non-GAMP-validated systems in the M&O zone. The OPC UA server is read-only. Or unidirectional to prevent information flowing from the M&O zone to the CPC zone. The historian channel carries data from the local plant historians and enterprise historian. This interface is also unidirectional. The second channel carries additional information from smart instrumentation in the CPC zone. This is auxiliary data from sensors and process analyzers. This may include additional process data such as temperature or instrument self-diagnostics. For instance, a flow meter may also measure process temperature. The measurement might not be utilized in the control strategy and may not even be calibrated, but can be useful in predictive analytics of equipment health. This interface is also unidirectional. Next, please. Right. So until today, most plants only have real-time process data from process sensors. But process data alone is not sufficient to predict equipment failure. So additional data needs to be collected from equipment in the plant, such as vibration, acoustic noise, and fluid levels in real time. So until today, technicians periodically collect this data manually using portable testers or reading mechanical gauges. This is insufficient for smart maintenance. Additional sensors are installed on the equipment and integrated into the analytics software. Wireless sensors are typically used for the additional measurements, because they are much easier to deploy in an existing plant. Sensors based on the wireless HART industry standards are easy to integrate with analytics and other software from multiple vendors using OPC UA. Next, please. The existing historian in the plant is part of the GAMP-validated system in the CPC zone. So making changes such as adding tags in the historian for new sensors or installing analytics apps using the data is not practical. Therefore, an independent aggregating server can be deployed in the M&O zone. The aggregating server also contextualizes data, meaning like logically grouping data that belongs together, coming from multiple systems, but grouping them together, for the same piece of equipment. Such an aggregating server, like a data lake, is optional. It may not be required for a small initial installation, but can be added later as the system grows, to more data sources. But it does not duplicate all the data in the historian. Next, please. Right. So edge computing and edge data storage is utilized whenever real-time prediction is required. That is, plant-specific M&O, data storage, computing, and software apps such as predictive analytics are installed on servers in the plant. Apps include equipment condition and performance analytics. For common equipment types such as pumps, and many more, there are ready-made pre-engineered analytics apps available using rule-based cause and effect, AI, and first principles. So no need for software coding or algorithm training here. So this is an easy and robust analytics solution for failure prediction and to optimize time of cleaning, for instance. For other use cases where failure modes and behavior are not well known, data science-based AI, such as machine learning with neural networks, can be used, to analyze historical data and maintenance records to create agents and models, in turn used with real-time sensor data to predict failure. Well, thank you.
Thank you, Jonas. Appreciate all of that. So we're going to move on now to a sort of case study or some real-time experience, real-world experiences from Janssen, and Niall is going to describe some of that for us. So Niall, please introduce yourself and talk to us about your experience at your organization.
Thanks, Tim. So my name is Niall Foy. I work for Janssen, which is part of the pharmaceutical sector of Johnson & Johnson. My role is manufacturing asset management, COE, asset management systems. So I work with the asset management systems and the business processes around that. Important to highlight what we regard as assets. So we not only think of physically installed assets, but we also think about our software. We think about our data. We think about our asset management processes. So they are assets as well for us, okay? Next slide, please, Tim. What I'm going to present here is the logic that we came to start our journey and to get us on this journey, okay? So building a sustainable asset management framework. Asset management strategies and processes are at the core for a successful maintenance and reliability organization. And I think everybody in the call will recognize this. Without the foundational building blocks of processes and people, right? So processes and people. It's very important that we keep an eye on the people in this as well, because a lot of the times we forget. We think about the technology, we think about the robots, we think about the end state being the most sophisticated, when sometimes, it doesn't need to be. But it's also very important that we have people who understand how to design and how to get us there. So investment in the technology is not likely to yield the desired results. So if we don't have the people and the processes, we're never going to get there. And again, all the sensors and smart devices in the world are useless unless we have a connected and collaborative asset management workforce, right? That values what they're reporting. Okay, so that's very important. Connected and collaborative asset management workforce. So this isn't just a technical role. This isn't just the maintenance teams or the engineering teams. This has got to do with our operations teams. It's got to do with our quality teams. It's got to do with the whole site in totality and how we work together. Next slide, please, Tim. The key components of our asset management program. So down the bottom on the right, we start with asset management processes. So what are the fundamental processes that we need, the business processes that we need to integrate into our business, into our everyday business, so that we can make a difference? Have we got the workforce competencies? So have we got an empowered, skilled, collaborative, and connected workforce? Empowered. Are we allowing our teams to identify innovation? Are we working with our teams to get at innovation? Are they skilled to drive that innovation? Digital asset management solutions and performance management. I always go performance management first in this when I present this slide, and the reason I go with that is because unless we can measure what we're doing, you saw the KPIs that Burkhard had presented earlier. If we start seeing what we can get in and what we can get out of our programs, the must-haves, the should-haves, and the could-haves, we can start measuring these things. We can start making a difference. Understanding what assets are performing, what assets aren't. Understanding what are the opportunities for improvement, what aren't. What's the business case? How do we build that? And then digital asset management solutions. For me, that's at the end. How do we have a robust business process? How do we have robust KPIs? How do we have a really connected workforce so that we can give a definition of a digital solution that we need? How can we improve how we're working with digital solutions? Next slide, please, Tim. This is the strategy that we have developed. It's the asset optimization strategy. And we've broken it into 3 pillars: asset data management, condition monitoring, predictive and prescriptive monitoring. And these are the 3 pillars. It reads from left to right. It's very aligned to the slide that Celine would have presented here with the maturity model, the digital maturity model. And what we have below that is we have the capabilities that we're focusing on. Now, these are a sample of the capabilities we're focusing on, and they're probably 80% of where we are putting our effort in. There are other bits that we are working on, but this is the high level stuff. So an example of this would be asset data management, standard business processes, connected asset health and performance management, integration of the CMMS and our PI historian, asset data quality and standardization. So the foundations, the real foundations so that we can move quicker. I was speaking with some colleagues and we were talking about we are going to implement a program in a project phase, system by system. The challenge we were setting ourselves is, can we change that to be, 80% of our time defining the business process robustly, and then the remaining 20% putting a digital solution in place so that we have a digital solution of a robust process, and then we can scale that product across other systems quite quickly. So that's the thinking we're putting in here. Below the capability focus, we've got the digital products. And inside in these boxes, what we're trying to show is the areas that we're working on. So we've got our CMMS, so computerized maintenance management system. We've got our engineering document and drawing systems. We've got our C&Q and our validation systems. We've got our process data, in-house apps. So we're developing our own in-house apps of how we're going to do things because we don't have a solution for our problem. And data visualization and contextualization of data so we can visualize it in a standardized way has been a substantial effort by the business and is really starting to pay results. If you read the slide from left to right, you'll see the maturity that I'm trying to display here. So the colors green versus blue, yellow versus blue, and pink versus blue. And you can see where we are in our maturity in those specific columns. So 2019 to 2025, that's their journey for asset data management. Our journey for condition monitoring, 2020 to 2030. Predictive and prescriptive, 22 to 2030 plus. So that's an evolving concept for us. Our value drivers, equipment and manufacturing reliability, capacity optimization, cost and value. Operations performance management. So that's our strategy, and that's what we tie our program against. Give the next slide, please, Tim. So this is an example of an area we're working on. You might say this isn't the most smart maintenance, but it is, right? And the reason this is because the standardization of the process, which is a large body of work, so that we can use advanced analytics. So if we can do this manually, you can automate it, and then you can use it in a quicker way. So calibration frequency optimization. We have 50,000 plus calibrations a year, okay, across the Janssen platforms. Leverage science and risk-based approach on existing calibration data, right? So we have a lot of data. How do we use our existing data to make decisions on how we maintain our assets? To determine the optimum calibration checking frequency. Optimize calibration frequencies, leading to significant reduced effort for calibrations and increased asset availability. Very important. Increase asset availability and the calibration effort. So reducing the workload on the technicians. Enablers, close collaboration, buy-in with quality or quality department. So how do we enter that conversation about we're going to use statistics to prove that our calibration program can be extended? We use a Wandelt analysis and we use a risk-based analysis. So Wandelt analysis takes a very defined number of test points, and it does a test to say, yeah, you can extend the calibration frequency of those types of instruments. And that's, we put a lot of effort into that. Workforce statistical skills and competencies. So how do we train people? How do we get people with the right knowledge? How do we get the right knowledge into our people and the competencies to use those knowledges and skills? Calibration process standardization. Again, if you're looking at this as a single site, you can have a standard process in a single site. When you're looking at this as many sites, how do we get a standard process across our platforms so that we can have one way of doing it and we can maximize our efforts with a digital product? The benefits, reduction of up to 40% of the calibration effort. So that's significant. So what we've been able to do is we've been able to reduce 40% of our calibration efforts. And if you look at, approximately 1 to 2 hours per calibration across 50,000, it's a lot of hours, okay? A lot of costs. Increase the asset utilization and availability. Again, we're able to give back the asset because we're not maintaining it, give it back to production so that they can fill that time with making more products. Reduction in safety risk exposure. So the less time you interact with the equipment, the less time you're putting your people at risk. Reduce risk of damaging during assembly and disassembly activities. So if you don't go at it again, you're not going to damage the equipment, right? Less usage of reference devices. So again, having the reference devices, maintaining reference devices, and that is a consumable in our process. Key to this, so we've standardized our calibration process. We've standardized our optimization process. We're now building a digital calibration frequency application that we can apply this data into that automatically and come out with the answers to see how we can extend our calibration programs. Very good. There's been a lot of progress made on that, but now how do we utilize that going into other forms of maintenance? So our PM programs, and that's where our focus is at the moment. Next slide, please, Tim. So the new skills and organizational approaches. I mentioned it before, it's the people, investing in the people, making sure we have the right skills, the right knowledge in our people, making sure that they understand the processes that we're trying to embed, asset characterization, condition-based and predictive maintenance, advanced analytics, sensor specification and vendor selection, advanced troubleshooting techniques, and Industry 4.0. A lot of time was spent seeing what we need to get into our teams so that we can do these transformations, so that we can get everybody on the same journey and align us all in our direction of where we're going to deliver. I'm not going to spend too much on this slide. Next slide, please, Tim. So the conclusion, it's a human-centric transformation. An innovation culture, learning fast, getting driving the impact. That's really at the core of what we're doing here. Building organization capabilities, competencies, and skills to accelerate value creation. unlock the potential machine health data beyond maintenance. So how can we take our very important maintenance data and how can we give that to our customers and to operations and say, hey, you know what? We're able to tell you how often we're using the equipment. We're able to tell you, we're able to predict when this equipment is going to fail or when we need to do maintenance. We're able to give you a deeper insight of how much you can actually reliably produce. A thriving partner ecosystem, key to transforming through differentiated manufacturing capabilities. So Celine mentioned it. How do we make sure that we have our vendor input? We've got people out there who are working in very specific areas. How do we get that information from the vendors back into our business and that key knowledge back into us so that we can partner is the best word to describe this, partner in that transformation and drive the business further.